Hey guys, it's Mr. Boyce. I'm going to go through this slideshow just in case you missed class or just kind of want to go over all of this before the test. So everything on this slideshow is something that will be on the test. So be sure to take some notes. Hopefully you have my notes that I gave you. But let's go ahead and get started. So for the first part is the slides for Hess's law. This is newer. So I'm not going to just like read all the slides to you, but we'll just go over it a little bit. So Hess's law is essentially just adding together different reactions. So you have this, it makes a little more sense if you can see it. So let's just kind of scroll to this reaction. Now, obviously, if we were doing it in class, it would have, all the dashes and the circles and stuff show up like one at a time. So it makes a little more sense. But let's just go ahead and work through what we got. Uh, so here, what I have is if you ignore the circles and the lines, we have carbon plus 1/2 O2 forming CO2. I know the 1/2 seems a little weird, but trust me, it makes sense because one of the most important things to take from this is you cannot change subscripts. Those are set in stone. That's what O2 is. And when you're trying to combine things, having different subscripts means you cannot combine them. So it is very important. Although it seems a little strange, it is important to do that. Okay, so in this case, we also have CO2 decomposing into carbon monoxide and 1/2 O2 or one oxygen. Now, just like in the ionics, when we had spectator ions, this is the same thing. So once again, ignoring the dashes over here in this was not here to begin with. So this was carbon plus O2 forming CO2. Now, if you go on both sides of the formula, what you can do is cross out these spectators. So in this case, CO2 in its entirety is on both sides of the arrow, and so that can be erased. Here we didn't have the 1/2, we just had O2, and then on this side we had 1/2 of an O2. So you can't completely eliminate what's in this yellow circle, but by crossing out the 1/2 O2 that was already here, and just look for the things in white for what's originally there, then we end up canceling out half of this O2 and end up actually having a 1/2 O2 on this side. So once we crossed out our spectators, then what we can do is just add those together. So the carbon was not eliminated. The 1/2 of O2 is still there, and the carbon monoxide is still there. So that's just adding together to get that. Okay, in this case, again, remember anything in blue or yellow is something that would have popped up organically as we were going through the slideshow, but this program doesn't do that. So in this case, we can add together the 2 moles of copper and the 4 moles of copper because they're both copper. And here we have 2 moles of O2, and so those can be just straight added together. For here, this is copper. Remember, oxygen is a -2, so this must be a +2. So this is copper 2 oxide. And then here, oxygen is a -2 as well, always. And this copper, since there's 2 of them, this would be a +1. And you have 2 of those. So this would be copper 1 oxide. So copper 2 oxide, copper 1 oxide. They are different, and so therefore you cannot combine the copper and the oxygen. So you would simply list that as 2 moles of copper 2 oxide and copper 1 oxide. Okay, so while you're adding them together, you're going to be given a target equation, and you are going to either reverse or multiply or divide to match that target equation. To do that, you can reverse an equation. Oops, keep trying to use my mouse there. Okay, and to do that, in this case, again, try and ignore the yellow and the blue for now. But if you see this reaction, this is a synthesis reaction between phosphorus and chlorine. And the delta H, or change in energy, is negative 574. So in other words, this is exothermic. This is releasing energy. Now here is the exact opposite. They reverse that. And when you reverse that, what you do is you change the sign. Okay, so you'll need to reverse, multiply, or divide equations to match your target equation. If you reverse, the point being you must change the sign. Okay, to multiply and divide a equation, the coefficients are the only thing you're multiplying or dividing. So again, ignoring the blue and yellow, if I had calcium plus two carbons to form calcium carbonate. And here, what I want to do is multiply this equation by 2. And so this would be, if there's nothing there, consider that a 1. So now this is 2. This gets multiplied by 2, so 4. Again, if there's nothing there, that's a 1. So multiply that by 2, you have 2. Because you multiplied the entire equation, you must also multiply the delta H by 2 as well, giving you a new delta H. Okay, this is an example of both reversing and multiplying. So in this case, this reaction is reversed. Okay, and just remember, it's very important that you understand these charges. I'm just kind of going to go over this again. Oxygen is always a negative 2. If you have 3 of them, that means 3 times 2 is 6. So you have 6 negative charges. You have 2 irons, so each one would have to be plus 3 in order to counteract that negative 6. So this is iron 3 oxide decomposing into 6 moles of iron and 9 halves of O2. Again, the halves seem a little weird, but just stick with me, it'll make more sense. And because I reversed the reaction, this negative becomes a positive. And because I multiplied everything in the reaction by 3, this number is also multiplied by 3, giving me a new delta H. So that's how you reverse and multiply, divide, same thing. You would divide everything by whatever number and then divide your delta H by the same number. So same rules apply. Okay, applying this to examples. Okay. Oh, here we go. Okay, so again, try and ignore the blue and yellow. Just think of it as not having that. So here, anything in blue and yellow will not be shown to you in a question. So make sure you get that. But here I have 1/2 of H2 plus 1/2 of Cl2 forming 1 mole of HCl. Okay, now remember, this is your arrow. This is very important. And when you write these equations, it's good to put the arrow in alignment just like this. It makes it a lot easier to add it. Okay, so what I'm going to do is I'm going to look for, as this note said, pick one substance that appears only in the overall equation. Obviously this big star is kind of covering this slide up, but it's going to be the same thing. This one's a little harder, so a pretty good example. So in this case, I have 1 mole of HCl, and what I want to do is match it to my target equation. This is the target equation. And so in this case, the HCl is on the correct side of the arrow. It's on the right side of the arrow. So I don't need to reverse this one. However, I have 6 moles of hydrochloric in here. I only have 1 mole. So what I need to do is multiply this equation by 6. Next, I've got N2, H2, and NH3. So here's NH3. Okay, and that appears right here. It's kind of better to go with the compounds. In this case, I have two NH3s. In this case, I have only one, so I know I'm going to multiply it by two. But also, this NH3 here is on the right side of the arrow. This is on the product side. And on my target equation, it's in the reactant side. So I'm going to reverse this. Okay, and then down here, you can see where that is reversed. So for this one here, for the first one, the negative 92, what I want to do is multiply that by 6, and that gives me this number. And for the second one, so this is times 6. And for the second one, I'm going to reverse and multiply by 2. And so reversing changes the sign, multiplying by 2 makes it 92 kilojoules. Okay, so if you just need the delta H, kind of good there to combine the formulas. Because I lined up the arrows, the 3 H2s that are on both sides, those are spectators, so you can cross those out. We don't have any partial eliminations like with the O2s. And so I'm going to add together 3 Cl2s plus 2 NH3s form 6 hydrochloric acids and 1 mole of nitrogen gas. And so that is how you solve those questions. Relatively easy. Just kind of think of them as a bit of a puzzle. Okay, and for this one, this is you'll see this question, and it'll be rather obvious because it's the only one that shows you these Lewis structures here. So what I want to do is count the number of bonds before and after. Now, I make it a point to constantly say that delta means final minus initial, and I stand by that, but I've also said there is one exception, and this is that one exception. So this is reactants minus products. So, you say you start with $100, you go into something, you leave with 50, you didn't gain 50, you lost 50. So this is kind of the same thing. What you start with, what you end up with, and what the change was between it. So for here, you have values for all of your different types of bonds. And this could also have double, single, and triple bonds and give you values. It just depends on the chart you're given. Okay, and what I want to do is count on each side of the arrow. All right, so there's our arrow right there. And so first is carbon, hydrogen. Okay, and I've got one here, one here, one here, 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 and here. So that's 1, 2, 3, 4, 5, 6 carbon hydrogen bonds. And so I'm going to go ahead and put a 6 here for my reactants, and here's my products. For carbon-carbon, okay, I don't have any carbon-carbon on this. Oh, yeah, I do. Sorry. So for carbon-carbon, call that this. I've got one here and one here. Okay, so let's go ahead and put that down. I have one here. Now you can do one side at a time or both sides. Both work fine. Doing this way may be slightly easier. It's kind of up to you. So let's go back real quick to the carbon hydrogen. I've got 1, 2, 3, 4, 5 on this side. I don't have 6, so this is carbon and chlorine. So let's just go ahead and put a 5 there. And for carbon-carbon, I've got 1 on both sides. Okay, next, chlorine-chlorine. I've got 1 here on this side. And on the product side, I don't have any chlorine-chlorine. So let's just mark that a 1 on the reactants and a 0 here. Okay, now for hydrogen-chlorine, on this side, I've pretty much counted every bond now, so I don't really need to look at the reactant side anymore. So let's just look at the product side. Do I have a hydrogen chlorine? I do. right there. So I've got 1 here and 0 there. And then finally carbon chlorine, which I do have right here. And so 0 on reactants, 1 on products. Okay, and then from there, what I'm going to do is just add 6 times 413, 1 times this, 1 times that. And then 6 times 413 plus 1 times 347 plus 1 times 239 is going to be 3,064 kilojoules minus my products, which is 5 times 413 plus 347 plus 427 plus 339. And that's going to come out to 128. Okay, and 3,064 minus 3,128 is negative 114 kilojoules. So that's your answer. And that's all there is to this one. You'll get a chart with bond enthalpies. All you need to do is look up here and look for those bonds and give yourself a kind of running count of what's on both sides and subtract the products from the reactant. So again, this is the one time I can think of where delta is not final minus initial. This is the one time that delta is initial minus final. Okay, on to stuff we've already done. Let's go ahead and look here. Now, before I start, I'd highly recommend you pause the video and you try and do this on your own. We have seen a pretty sharp drop in test scores lately, and I think a big part of that is if you look at a question on like AI and you see the question worked out, you're going to look at it and go like, oh, that makes sense, cool. But it's a lot harder to cold answer questions if you are doing that. So everything I'm about to show you will probably totally make sense to you, which is great, but make sure that you're able to cold answer these. And the only way you can really do that is to try and do this before I show you the answer. So enough lectures, let's get to it, and I will show you the answers for these. Okay, so how much heat? Now, the important thing is this says in calories, and I guarantee people are going to get this wrong because of that. It's needed to rate this temperature. So I have a mass, I have a C of lead, all right? And notice this C is in joules. That's very important. And I have a delta T. So I've got an M, I got a C, I've got a delta T. This is going to be a Q equals MC delta T. And remember, the important part is being able to cold answer these. So you need to be able to read these questions and know what formula to use. The formulas are on your formula sheet, but still you need to know when to use them. Okay, so in this case, I'm going to do MC delta T. So that's going to be 125 times 0.130 times final minus initial. Remember, that's pretty much always the case, except for that one earlier one. So 41.1 minus 17.5. And if I put that into my calculator, I'm going to get 384, and that is going to be in joules. And remember, my question is asking for calories. So obviously 384 would probably be one of the 4 multiple choices on the test, so don't fall for that. So let's convert this from joules to calories. And 1 calorie is equal to 4.18 joules, which is also the C of water. That's the one C that you do have to have memorized. And so my final answer for this one is 384 divided by 4.18, which equals, running out of space here, 91.7 or 91.7 calories. Okay. Okay, for this one, again, Q equals MC delta T. Now, in this case, I want to know the final temperature of a sample. I have a C, I have a Q, um, and I have a number of grams. So that gives me my M, and I have my initial temperature. So the easiest way to solve for this is if I need the final temperature and I have the initial temperature, then I'm solving for delta T. Okay. And to solve for delta T, what I'm going to do is rewrite this equation as delta T equals um, Q, what that's a G, was Q divided by MC. So let's rewrite it like that. And let's see if I can pick a color that's maybe a little easier to see. Okay, so Q is 328 joules. M is my mass, which is 16.7 grams. And my C is given to me at 0.54. Okay. Now, if I put that into my trusty calculator, I'm going to get a 36 degrees Celsius as my delta T. Be careful, this is not the final answer. Remember, delta T equals temperature final minus temperature initial, and we want temperature initial. Now, because we did this math, we now have a delta T, which is great. So 36 equals temperature final. I'm sorry, we want temperature final. So temperature final is X minus temperature initial, which is 24.4. So therefore 36 equals X minus 24.4. And so X equals 60 degrees Celsius. So 60 minus, or yeah, 60 minus 24.4, or this is the rounded answer is 60. Okay. For these, what you're doing is you are using this as a conversion factor. So I'm going to go through this, and again, nothing too terribly difficult on these other than I would say the hardest part really is looking at the questions and just knowing what to do. If you know what to do, then they are pretty easy. So that's really kind of what you're studying here. The numbers I give you on this aren't very relevant. It's just a demonstration. Okay, so carbon dioxide can be formed from the reaction of carbon monoxide and oxygen. How many moles of carbon monoxide must be reacted in order to produce 147 kilojoules of energy? So to produce, that means I am having to lose that energy from the system. So very important you're reading the wording on this because this is not 147 kilojoules, it is negative 147 kilojoules. Okay. Now from here, I can use this as a conversion factor. Okay. This is for the overall reaction. And for the overall reaction, we want moles of carbon monoxide. And so this says for every 2 moles of carbon monoxide, your delta H is negative 787. So kilojoules comes down, as always, whatever goes up must come down to mole. And so negative 787 for every 2 moles of carbon monoxide. If I was going for O2, I would have put a 1. If I was going for CO2, I would have also put a 2. But this asks for carbon monoxide. Okay, and in this case, I want moles, so I don't actually need to go any further. So in my calculator, negative 147 times parentheses 2 divided by negative 787. Negative times negative is a positive, so your answer here is 0.374 moles of carbon monoxide. Here, basically the same thing, just a little bit more conversions needed. So how many grams of oxygen? So I want grams of oxygen, that's important, are needed to react with excess methane. Excess just means you don't have to worry about it. It's not a limiting reactant thing. Uh, in order to produce, so this says produce just like the other one did. It won't always say that. Sometimes, it could be to, uh, bring in amount of energy, something like that. Um, So to produce 505 kilojoules, so negative 505 kilojoules. Okay, and so always start with the given measured quantity. So kilojoules per mole. In this case, for this reaction, negative 890.4 kilojoules. And again, we want grams of oxygen. We don't have that yet, but we do have moles. And this has a 2 in front of it. So in the case of oxygen, I am going to put a 2, whoops, 2 moles of O2. Now, if I wanted it in moles like the previous question, I'd just do my math, but I don't. I want it in grams. So whatever goes up must come down. Moles of O2 to grams of O2. And 1 mole of O2 is 2/16, so that is 32 grams per every mole of O2. And so negative 505 times parentheses 2 divided by negative 890.4, close parentheses times 32, that is going to come out to 36.31. Okay, and here we go for this one. You are, again, as most of the time, you are between final minus initial, so products minus reactants. This looks a little scary, but all this is saying is delta H equals the sigma, which is sum. So you add together, N is moles, which is your coefficient, and delta H formation is a chart value. And remember, anything in its elemental state has a delta H of formation of 0 because you do not have to form those. So that is any individual element, like a metal is the most common, like copper, iron, something like that, or a diatomic. So you have your 7 diatomics, including O2. Sometimes it's on the chart, sometimes it's not. And so O2 is 0. Now, what I want to do is final minus initial. So I am going to just take a look here. I've got CH4 is negative 74.8. Here I've got 0. Here I have 1 mole of CO2, and CO2 is right here at negative 393.5. And here I have 2 moles of water, so 2 times water, which is negative 285.8. Okay, and what I want to do is final minus initial. So I am going to swap that. Let's see. Okay, so I am going to swap this and do in my calculator. Let me go ahead and grab one real quick. Final, which is going to be this. So, sorry, I already have that. Just a side note, whenever you grab these calculators, I noticed some people getting wrong answers. Make sure that you hit the second and then 0 for reset, and then scroll over to yes, and it'll say memory cleared. I do this as a habit every time I pick them up. I saw people put in everything right and still get the question wrong because of some setting on the calculator. So don't let that happen to you. So anyway, parentheses negative 393.5 plus uh, plus 2 times negative 285.8, enter, and that is going to be uh, negative 965.1. Okay, and so this here is CH4, that 78.4. And so final minus initial is going to be negative 965.1 minus negative 74.8. So minus negative 74.8. This is where paying attention to your signs is very important. And that's going to be negative 890.3. Where you are with that on my notes. Hey, 1 second. Let me just double check this and make sure that I'm not putting the wrong thing on the video. All right, so final minus initial, I got CO2, that's negative 393.5 plus parentheses 2 times negative 285.8, close parentheses, negative 965.1, perfect, minus 1 mole of CH4, which is negative 74.8, which equals negative 890. Okay, confirmed. So that is the correct answer. Hey, and this is in kilojoules. So if for some reason your question asks for something like joules, make sure you convert it. Okay, what temperature is this substance at its normal boiling point? So when we say normal, that's going to be at 1 atm, which is right here. Now, notice this is solid, liquid, and gas can cover pretty broad range here, depending on pressure. Even very cold things can be gas. Okay, now in this case, I'm going from solid. Whoops, this is the point where I would go from solid to liquid. And so this would be the melting point going from solid to liquid. Now, this just lists a couple of temperatures here. So you kind of have to estimate a bit. And so here, we'll say that's about 57 or so, just less than 60.8. Next, at what pressure does a triple point occur? So let's just pick that. This is our triple point right here. And the pressure for the triple point is 0.24 atm. Celsius. Okay, and then the other thing to pay attention to is at the triple point, what's going to happen if I manipulate variables? In this case, the pressure. If I increase the pressure from the triple point, then notice I'm going to end up in the liquid phase. If I decrease the pressure, I'm going to end up in the gas phase. As far as temperature goes, same thing. You can move your dot around and see what happens to it. So let's say, I'm somewhere in the map, like right here. I can look at this and see, okay, if I increase the temperature, or what's going to start to happen, okay, here's a phase change. If I decrease the temperature, at what point is it going to phase change from, say, this pressure? And then you can scroll down and estimate that temperature. So it's going to ask you questions that look like you need to use math, but really all you need to do is look at this graph and just estimate. It'll be a multiple choice, so just pick the ones that's closest and you'll be fine. Okay, last but not least, let's go over this one right here. Now, you may or may not have to go through and go all the way from a negative number to a above 100 degrees, but let's just go through all of them so you know how to do it for sure. Okay, in this case, I want to go from negative 15 degrees Celsius to positive 145. So sub-zero ice to steam. I've got 72.3 grams of ice or water, and I want to calculate the total number of heat in joules, which is very important, to accomplish this. You have two formulas for this. You have Q equals MC delta T, and this is for the delta T's. So Q equals MC delta T. This is going to be here, here, and there, anytime you have a change in temperature. This is a phase change right here. Let's just change the color of our ink for these. So um, these are phase changes. And for these, what you need to do is use your delta H, and you're going to use that as a conversion factor. This is the pretty much just like we did before with the other delta H's. So this is why we did stoichiometry first, so you would be comfortable with using things as conversion factors. Okay, so first off, what we want to do is go heat the ice from its heat from ice to its melting point. So that means I want to go, let's go with blue, since this is a QMC delta T. I want to go from negative 15 to 0. So Q equals MC delta T. I need the energy, so I'm solving for Q. So Q equals MC delta T. So M is mass, which I have right up here. That's going to be 72.3 grams times C. Now remember the C of water, you have to know that. That is 4.18 joules or 1 calorie if you're wanting to solve for calories. So the C of ice is 2.01 joules. Okay, and then times your delta T, final minus initial. So my initial was negative 15, my final is 0. So 0 minus negative 15 is a positive 15. Okay, and that equals 2,180 joules. So 2,180 joules. Okay, next is energy required to melt the ice. Okay, and that is going to be your delta H of fusion right here. And so for that, what I'm going to do is use this as a conversion factor. So I know it takes 6.01 kilojoules. This is important, kilojoules per mole. Okay, so if I have a mole, I can work with that. So I do not have a mole, but I do have 72.3 grams of H2O. Whatever goes up must come down. Grams of H2O to mole of H2O. And 1 mole of water weighs 18 grams. Okay, now mole of H2O. And this is where I can use this conversion factor, 6.01 kilojoules per mole. Okay, so 1 mole requires 6.01 kilojoules. Now, if I do my math, I would cancel out moles, I would cancel out grams, and be left with kilojoules. However, I can't really add kilojoules when everything else is in joules. So let's do one final step. Oops. And convert kilojoules to joules, and that's 1,000 joules for 1 kilojoule. So in my calculator, 72.3 divided by 18 times 6.01 times 1,000, and that's going to come up to 24,100 joules. If you can do those, you're good. The rest of them is just sort of repeating our work. So now what I want to do is go from 0 to 100. Okay, and to do that, I'm going to do Q equals MC delta T. And so, oh, let's go back to blue. And so I'm going to do 72.3 for my M. C is going to be water, which is 4.18 for joules. And my delta T is final minus initial, so 100 minus 0 is 100. Okay, and if I put that into my calculator, I'm going to get 30,200 joules. Okay, energy required to vaporize water. So this is the same thing I did up here. The only difference is I have a different C value. So let's just go ahead and run through the whole thing anyway. So let's start with 72.3 grams of water. Let's convert grams of water to moles. And that is 1 over 18. Okay, and in this case, this is delta H of vaporization. And notice this takes considerably more energy, 40.7 kilojoules per mole. So let's put this in here, 40.7 kilojoules per 1 mole. And again, you can, if you want, where it says kilojoules, just call it 40,700 joules. I mean, if you want to do that in your head, that's usually what I do. But just to point out the importance, we do need to convert kilojoules to joules one way or another. And that's 1 over 1,000. Remember, always use the 1 for your larger unit. So, whoops, kilojoules is obviously larger than joules. That was an ugly J. Okay. 72.3 divided by 18 times 40.7 times 1,000 is 163,000. Of course, I'm rounding these by quite a bit. Okay, and finally, let's do one last. Now we want to go from steam at 100 degrees Celsius to steam at 145. So Q equals MC delta T one more time, and that's going to be 72.3 times. Now remember, the C of steam is not the same as the C of water, although obviously it's extremely close to ice, but 2.02 joules, which is great, means I don't need to convert kilojoules to joules. Okay, and so that was times 2.02 times my delta T, final minus initial, 145 minus 100 is 45. And if I do that, my answer is going to be 6,570, which means total energy in joules is going to be just simply adding these numbers together, and that comes up to 226,050. That's kind of hard to read. Okay, and so that is going to be my final answer. All right, my friends, that is it. So, make sure that you are also going through your notes, going through your textbook. If you look on Google for videos, I highly recommend Tyler DeWitt. He has amazing videos. But remember, it's an advanced class, so the expectation is that you're not just listening to the lectures and taking notes, so you are also studying. So you do need to be using your e-text and whatever other materials. So, but most importantly, your e-text. If you have any questions, let me know, and good luck on the test. You got this. Thanks.